This is Sunghyon JANG from Graduate School of Engineering in Osaka University. Today, I'd like to talk about new experimental methodology for simulating self-wastage phenomenon using simulant materials. First of all, I'd like to introduce you about what exactly the self-wastage is. In a steam generator of a sodium fast breeder reactor, there exists the leakage sodium and water vapor through a thin heat transfer tube. Therefore, if a tiny through-wall defect occurs at the surface of the tube, high-pressure water and vapor will leak into the sodium side and sodium-water reaction will take place. If a sodium-water reaction continues, small leaks will suffer self-damage and grow, resulting in a sudden increase in leak rate. And this is called self-wastage phenomenon. And the self-wastage will continue for a period of time. The increased leak will damage the surrounding tubes, bring secondary failure of steam generator tube. So, it is very important to evaluate the leak detection capability of initial leaks before they become larger leaks, and to know the time to sudden enlargement under various steam generator operating conditions. So we focus on the maximum size of the enlarged leak to evaluate the leak rate and quantify the increased rate to assess the time for the sudden enlargement to be initiated. So far, in order to evaluate the self-wastage rate, experimental approaches such as Swartford Marker test have been carried out. However, it has limitations. So we suggest a new method to evaluate the self-wastage phenomenon through an experiment using simulant material. So from now on, I'd like to introduce you about the concept of the new experiment methodology. Since the self-wastage is attributed to the chemical reaction which takes place in the vicinity of the leak, we decided to adopt hydrogen chloride and sodium hydroxide solution and paraffin wax as a simulant materials. By injecting hydrogen chloride into sodium hydroxide through the paraffin wax nozzle, we will perform the neutralization reaction in the vicinity of the outside of the nozzle. Then, we will evaluate the maximum size and the shape of the enlarged nozzle by the reaction heat. As the first phase of the study, a numerical simulation has been carried out in order to validate the feasibility of this new method and decide the experimental conditions. And this slide shows initial boundary condition and assumption for the analysis. So from now on, let me show you the results of numerical simulations. Through numerical simulation, we could visualize the temperature of the surface wax around the nozzle and evaluate the temperature distribution at the surface. The results show that the surface wax in the vicinity of the nozzle would be melted by the reaction heat so that the nozzle would be enlarged. By considering the front and the side view of the temperature near the nozzle, we could also expect that the nozzle would be enlarged dominantly toward the direction of the length rather than the direction of the width. Let me conclude this presentation. So in this study, we propose a new experimental methodology for simulating the self-wastage phenomenon by using simulant material. And the feasibility of the new experiment was evaluated through numerical simulation. And the following things are expected from the numerical simulation result. For the future work, we will calculate the self-wastage rate using heat transfer coefficient, and we will evaluate the time to sudden enlargement take place by considering the self-wastage rate. And thank you for your attention. I hope I have a chance to explain about more detail about my research on FR13 in Paris.